Okay, let's go through the theory behind SLAM-seq. SLAM-seq is a metabolic labeling technique used to determine the half-life of all mRNAs in a cell. In other words, it tells us how stable or unstable different mRNAs are. Understanding the half-life of transcript can help you gain insight into how cells respond to different environmental clues. For example, in a recent paper from my group, we showed that mRNAs encoding for ribosomal proteins are extremely stable in neuronal stem cells, and this impacts their capacity to divide. To calculate the rate of RNA turnover, at the end of the day, we'll need to be able to differentiate between what is newly synthesized and what is old mRNA. So for example, let's say we have at time 0, one gene expressed with this promoter, and this promoter would have generated a number of transcripts. And then we want to see at a later point what happened with these transcripts. So we have the same gene at a certain time x with the same promoter that is producing now at a later point new transcripts that we have here in pink, and some of the transcripts that we had before remain in the cells because of their stability. So we have here a bunch of transcripts, for example, that can go to decay, and we have another set of transcripts that are carried over through time, and we have these transcripts that are being newly synthesized. Okay, so how can we differentiate the old from the new RNA? One possibility is to stop the synthesis of new RNA altogether using, for example, Actinomycin D, but this causes a problem because we are effectively killing the cells, and this stimuli can also disrupt the rates of RNA synthesis. So for example, if we stop the synthesis of RNA, we wouldn't have these transcripts, and we will know that of the whole pool, these transcripts that are present came from the previous state. Alternative to stopping the transcription is to label the RNA metabolically. So to do that, we add to the media some modified nucleotide that can be incorporated into the mRNA. So all of these mRNAs will have a bunch of these modified nucleotides inside their transcripts. So once we have all our transcript labeled, we just stop the labeling, and then when we go to time X, only the old transcripts will have the nucleotide incorporated. And we will be able to distinguish the old from the new by the presence of these modifications. Stopping transcription was bad for the cell, however, adding modified nucleotides is not great either. You need to add as little as possible. However, you may be left with too few labeled transcripts, and this is problematically, especially for the original metabolic label approaches. So the older methods, you have the RNA, and you have, for example, the incorporation of a modified U here and there. Here, let's say we have it in 4 different places. And then when you do the RT conversion to cDNA, this U in most cases is converted to T, or transcribed into T, and only in few instances you have mutation of this modified oligo. So you added a lot of nucleotide, but in this process you lost a lot of the signal, and this was problematic. So this is where the innovation of SLAM-seq come into play. So again, you have your RNA that will be metabolically labeled. So you have the uracil mark here and there. But this time, instead of going directly for the RT reaction, what you do is to add a chemical that will react with the base and will further convert it into another modified nucleotide. So instead of the star here, we can say that these U's have a hat now. And it's now when you have this further modification that you do the RT to get the cDNA, and you get that most of the original incorporated modified nucleotides are actually reflected in the cDNA. So SLAM-seq innovation comes in improving this last step. Now let's see how a typical SLAM-seq protocol would work. So you will have your timeline here. This is time in hours, let's say. And what you want to do is, for the first 12 hours or so, this will depend on the cell type, add the modified nucleotide to your media in such a way that you have initially all of the transcripts that are not labeled. But at the end of the 12 hours, you will have as much conversion as the cell would tolerate. This will be the transcripts with the modifications. And then what we are going to do to fit the decay model is to take several time points. We can take typically 3, 6, 12, and you can add some other time points. That's a pretty standard protocol. So after 3 hours, we will have our transcripts that probably most of them already lost the modifications and they have been replaced by new ones. Then at 6 hours, we'll have a further decline. So maybe we have one here, and by the time we reach the 12 hours, there's no modification left there. So now we want to understand how this decay process is taking place. So if we go ahead and we sort of plot the old mark RNA, we will have a curve that goes like this rather than having a straight line. So we will have initially some values up here at 0. That will be our maximum number of modified or all transcripts, and then they will be gradually disappearing, but mostly following this sort of trajectory. So in that case, what we have is that the slope of this old RNA, according to the time in hours, is not like a constant, but rather it depends, this decay rate, on a constant that is proportional to the amount of the RNA that we have at that time. We can say like the rate of RNA decay over time is equals to a constant time the abundance of the RNA at that time, and this equation is solved, or once a solution, the solution for this equation is this, because when we derive e to the x, we have e to the x, but since the x or the t here is multiplied by k, due to the chain rule we have to bring down the k, and so this is the solution. So the idea now is to take our raw data and fit it to this exponential decay to obtain this k value, and from there we will have an idea of the half-life. So now we can fit our model to this exponential decay, and the video in the link provides a step-by-step approach and code to do this. Okay, now that we have the model and we obtain the k parameter for fitting the data, we will calculate the more intuitive half-life value. Once we have our k, we have that the function is the RNA over time is equal to e, and we will put a minus because we want to keep the k positive, and we know that the exponential decay is negative. So we have this function, we know the value of the parameter k, we know that at r0 this will be 1, and that our half-life time, that we denote as time x, we will have half of the original amount. In other words, 1/2 will be equals to e minus k and the time x that we want to figure it out. So if we do the logarithm in both sides, we have that the log of 1/2 is equals to minus k times the half-life, and this is the same as log 2 divided k, and that is our half-life. Okay, that's it for the SLAM-seq overview. If you find it useful, please subscribe to the channel, and to dive deeper into the analysis, you can find all the SLAM-seq videos on the screen now, and I will see you there.